All right, so let's go ahead and get started. So today we're going to be continuing with what we talked about last time, and that was one-dimensional kinematics. So I want to start out by just laying out all of the equations that we're going to need in order to solve these problems with one-dimensional kinematics. So the first equation says that Vf is equal to V0 plus plus A times T. Second says Xf is equal to Xi plus V not, and actually they usually use i's here, so I'll try to be consistent with the notation. VIT plus 1/2 AT squared. Then we have Vf squared is equal to Vi squared plus 2A delta X, where delta X is going to be Xf minus Xi. And the last one says that delta X is going to be equal to 1/2 Vf plus Vi times T. Okay? So we went over how we applied these equations to solve various problems last time, but at the end of last class I believe that I had solved the problem, but we hadn't had much practice with these problems yet. So today what we're going to be doing is spending almost the entire time just working on problems applying these equations, both for one object as well as two objects. And we see that actually when we do these with two objects, it's basically the same thing. We just have a duplicate set of equations. So you have one set of equations for one object, one set of equations for the second object. So let's go ahead and look at our first problem for today. So first problem says a truck covers 40 meters in 8.5 seconds while smoothly slowing down to a final speed of 2.80 meters per second. Now when it says smoothly slowing down, what that means is it has a constant acceleration or constant deceleration in this case. We want to find what its initial speed was, or its original speed, and find its acceleration. So go ahead and talk to each other about this one, and then we'll go ahead and solve it. So let's talk about this one. So we're told that a truck covers 40 meters in 8.5 seconds while smoothly slowing down to a final speed of 2.8 meters per second. So let's kind of draw what's going on here. So we have our truck here. So, and this is going to cover some distance. For now, I'm just going to call it some distance x, or ultimately it's going to be some delta x. And the reason why you can call this delta x and say x and delta x are the same thing is if I define a coordinate system, so this is 0, you're subtracting, you're doing xf minus xi, but xi is 0. So you can say that. So this is going to cover this distance in some time, where that time is going to be 8.5 seconds. And this distance here, what was this, 40 meters? It's 40 meters. And when it gets over to here, it has some velocity Vf, where this Vf is going to be equal to, this is going to be equal to 2.8 meters per second. Okay, so in drawing this diagram and labeling everything, I'm already laying out what things I know and what things I don't know. There are two things that I don't know that I hadn't listed here yet, and that's the initial velocity. We don't know the initial velocity, and we don't know the acceleration. So when I'm looking at this list of equations that I have, I know for the first part what I want to solve for is the initial velocity. So we can go kind of line by line and ask ourselves, can I use this equation in order to solve for the initial velocity. So if I look at this one, I can't really use this to solve for the initial velocity because I would need the acceleration. Same thing with this one. Same thing with this one. So the only equation that I can actually use is the last one that relates delta x, vf, vi, and t. And so when I look at this equation here, I can say that delta x is going to be equal to 1/2 vi plus vf times t. And what we want to do is solve for vi. So what I can do is I can multiply both sides by 2 over t. So that's going to cancel that on this side. So this is going to be 2 divided by t times delta x is equal to vi plus vf. And then I can subtract a vf from both sides. And when I do that, I see that vi is going to be equal to 2 divided by t delta x minus vf. And then when I plug the numbers in for these, so I have the time here, I have the distance that this covers, I have the final velocity. When I plug the numbers in, I'm going to end up finding that this is 6.6 meters per second. Okay? So now that we have this now that we have this initial velocity, what we'd like to do is we'd like to find what the acceleration of this is, or in this case the deceleration over the interval that this travels. So in order to do that, we could actually use any one of these three equations because now we have the initial velocity, we're trying to solve for the acceleration. But one of these is a better choice than the other two because it's going to be simpler to calculate, right? So if I look at these, the second one, I'm going to have to square time when I plug it in my calculator. I'm going to have to square velocities in this one. So what's actually easiest is just to look at the first one. And so if I want to solve the first equation for the acceleration, what I do is I can move this initial velocity to this side. So I have a vf minus vi is going to be equal to at, divide both sides by t, and so a is going to be equal to vf minus vi divided by t, and this is going to give me a value of negative 0.45 meters per second squared. Okay? Not too bad, right? Any questions about this? All right, so let's move on to another one. So these are going to progressively get a little bit harder. Okay, well actually this one's kind of a big jump, but go ahead and read this one and then talk to your neighbors about it, and then I'll come around and answer questions. This is a case where you have two objects moving and you want to find where they're going to be when they intersect each other and how long that takes. Okay, so let's go ahead and solve this one, and then we'll move on to another one. So it's a little tough to start out with, but I think as we go through this, and now that you've worked through it a little bit yourself, you'll start to see kind of a pattern for the way that we're solving these questions in terms of the way that we choose our equations, as well as the way that we're going to kind of pick off terms that we need from the diagrams that we draw. So the first thing that I want to do here is I want to draw a diagram representing Jimmy and David as they're moving here. And so what I want to do first is to draw some arrows representing their velocities, and also define what direction I'm saying positive and where 0 is. And this is very important because what we need to do ultimately is to write equations for their positions in such a way that we can solve for the time. And so in order to do that, first I'm going to draw, this is the distance that they're separated. This is 3 miles, which is about 4,800 meters. This is Jimmy. This is David. Okay? And I'm also going to say that this is the positive x direction. So define a direction that you're going to say is positive. Also define where you want to put the origin. I'm going to put my origin where Jimmy is. Okay? And the reason why I'm doing this is when I define my origin, when I define my direction, that's going to change the way that I represent these these terms in this equation. And we'll see that in just a second. So let's first write Jimmy's equation. So I'm going to write some position equation for Jimmy, where this is going to be equal to, well, what is his initial position? We can just read this off term by term. What's his initial position for the choice of origin that I have here? 0, right? He starts from 0. And then he's going to be moving, is this in the positive or the negative direction? Positive direction. So this is going to be some positive initial velocity. I'm going to do is v sub I d, so this is, or sorry, v sub I j. So this is Jimmy's initial velocity, times the time, plus the acceleration that he has. But he's moving at some constant velocity, and so this acceleration is 0 plus 0. So our Jimmy equation, x sub j, is going to be equal to v sub I j times t. Okay? Now we want to do the same thing for David. So for David, we say that x sub d is going to be equal to. Now, what is David's initial position? Again, relative to the coordinate system we have. So we say that this is where 0 is. So David's initial position is this 4,800 meters, and I'm just going to give this some x0 for the time being. I'll plug in the numbers later. Now we got the initial position term for David. We need a velocity term. So when we're looking at the velocity term, is this going to be positive or negative? Negative. So this is going to be minus vi d times t. Again, no acceleration. And so these are the two equations that we have. Now, at some point in time, if they're moving like this towards each other, they're going to end up being in the same place. You can just put that place here. And so what that means is if this represents David's, or sorry, Jimmy's velocity, and I can say, or sorry, position. I have another arrow that can represent David's position, and if they're in the same place at the same time, what that means is that xj is equal to xd. Okay? And so what that allows me to do is it allows me to set these two equations equal to each other. So v I j t is equal to x0 minus v I d t. And now when we look at this equation, the only unknown that we have is the time. We know the initial velocities, we know what this initial position is, we can solve this for time. We see that the time that it takes for them to meet is going to be equal to, this is going to be equal to x0 divided by vij plus vid, which is equal to, I believe, somewhere around 944 seconds. Okay? So now that we have this time, we want to find how far from David's apartment do they meet. And so in order to find how far from David's apartment they meet, it's a little bit tricky with the way that I set up the equations. But really, for the way that I set this up, if I wanted to find the distance from here, what I need to do is I say, well, David's going to travel 4 meters per second for this time, 944 seconds. And so the distance from David's apartment, because right now I'm measuring everything relative to Jimmy's apartment. The distance from David's apartment, I could write xd is going to be equal to vd times t, or v sub 0 times t. And when I plug this in, I end up finding that this is 377 meters. Okay? Any questions about this? We're gonna get quite a bit more practice with these ideas, but I think hopefully you guys are seeing kind of the pattern or the way that we want to go about thinking about this in terms of we have our equations, we kind of pick off the equation or the terms that we want per the definition of the coordinate systems and the positive and negative direction. Okay, so let's look at another one. Okay. So this one's not two objects, but what it is it's one object that has two different intervals for the way that it behaves. So go ahead and talk about this one, and then we'll talk about it afterwards. So let's go over this one. So when you do these problems, I saw one mistake that was fairly common for finding what the total distance was, and that was to say that the total time is some time 3 minutes and 16 seconds, which is 196 seconds plus the 4.8 seconds. But there's a reason why you can't do that, and it's because the motion of this jet is really broken up into two pieces that are separate from each other, in the sense that for this piece, the jet is going to be moving with some constant velocity, and this piece right here, the jet is going to be accelerating. And so we're going to actually have two different equations to describe the position versus time for each one of these. So for the first one, what we can say is the position versus time has no acceleration, right? Yes. For this one, we have to include that acceleration term, and so because of that, we can't just combine it into one time interval. We have to break it up into two time intervals. Okay, so let's see how we can calculate what the acceleration of the Afterburner is here. And so in order to do that, we're told we have some initial velocity of, I believe, 96 meters per second, and final velocity of 154 meters per second. And so we want to find what the acceleration is. We also know how long that takes it to change its velocity. So that takes 4.8 meters per second, or sorry, 4.8 seconds. And so based off of that information, we know that we can use this equation because we know everything in it except for the acceleration. And so we can rearrange this to say that the acceleration is just going to be the final velocity minus the initial velocity divided by the time. And when we do this, we get something that's about 12 meters per second squared. Okay. Now, when we go to find what the total distance is here, a lot of people use this equation. That's perfectly fine. You can use this equation, but you have to be careful if you're going to do this, because if you're going to do this for this interval, the initial velocity and the final velocity are the same, right? Because initially, or this interval 1, let's say, the velocity doesn't change. So initial is the same as the final, and the time is the 4.8 seconds. Oh, sorry, this is the 3 minutes and 16 seconds converted to seconds. And for this one, we say that it has some initial velocity, which is the 96 meters per second, and it has some final velocity, which is 154 meters per second. And that's going to occur over a time interval of 4.8 seconds. We can calculate that and then add them together. So that's one way to do it. The way that I did it actually was to use this equation. And so when we use this equation, we can pick off the terms that we need for interval 1 and interval 2. So for interval 1, what we can say is x sub 1 is going to be equal to the initial position. So this is the initial position we have here, plus the velocity, or the initial velocity, vi, times the time, plus the 1/2 times the acceleration times time squared. Here, it's not accelerating, so this is all we have. So we can find this position, or this distance that this travels, by just multiplying the velocity that we have times the time that it has that velocity. And so when we do that, I don't know if I wrote this out in steps. I don't know if my answer is right. So you can do that to find this distance x1. Okay. So then we can do the same thing for this one, and that's to say that we could say that this starts from 0 here and find this distance that this covers. And this is going to say that this is x2 is going to be equal to v1t, the same velocity that we had for this interval, the 96 meters per second, plus 1/2 at squared, where this time is the 4.8 seconds. Okay, and you can see that we had to break this apart. Now to find the total distance this covers, this is x1 is x1 plus x2. And I don't know that I trust the number that I have here. I might have typed it in wrong, but this says 82,000 meters. So this is probably wrong then. I don't know how to use a calculator. Okay. But the important part is that you realize you have to break this apart. Now, otherwise, you could use this equation here, and you'd get the same answer, but again, you have to break this into two pieces for the two different time intervals. And so this is probably wrong. Okay. All right. Any questions about the process that we went through here?
Do you have the final answer? Because I'm not sure.
I can check it.
Okay.
But let me do that while we're working on the next one. Okay. Okay. So the next one's actually going backwards a little bit. This one's a little bit easier than some of the other ones. But you have to take into consideration two things here. We know that this is moving under the influence of gravity. So it has a known acceleration. So the acceleration due to gravity, conventionally we say is negative because we say up is positive, gravity acts down. So the acceleration due to gravity is going to be minus g, which is minus 9.81 meters per second squared. Okay? And the other thing has to do with what happens when it reaches the highest point that it's going to get to. Okay? So think about those two things, and I'll do that calculation again to check it.
Remote on that camera?
Do I have what?
A remote?
Yeah, it's not plugged in right now though, like the slide changer.
All the time?
Oh, this? Yeah, it is actually. Okay, so let's go ahead and talk about this one. So we have a ball that's hit up in the air, and I need to remember what we're told here. So it takes 3 seconds to get to the top, or the highest that it's going to go. So this is 3 seconds to get this high. And the first thing that we want to find here is what the initial velocity of the ball is. And so in order to find the initial velocity of the ball, we actually know two things about this situation without explicitly having numbers. The first thing is that the acceleration, A, is going to be equal to g, or negative 9.81, okay? And this is meters per second squared. And when it gets to the top, what's our velocity going to be? 0, right? And so what that allows us to do is it allows us to use this equation. So we have Vf is equal to Vi plus At. This is 0. This is 9.81. We can rearrange this so that we have Vi is equal to 9.81 meters per second squared times 3 seconds, and this is about equal to 30 meters per second. Okay? So then what we want to do is we want to find what the maximum height is, or how high this ends up going. And in order to do that, what we can do is we can use this initial velocity in conjunction with the second equation. So xf is going to be equal to, we can say the initial position is 0. We'll define where it starts to be 0. So then xf is going to be equal to VIT plus 1/2 AT squared. Plug in our initial velocity, our time, our acceleration, which this is minus 9.81. And when we do that, we end up finding that this is about 45 meters. Okay? Pretty straightforward. Okay. So now we're going to go to another one where we have two objects. So I think we're getting a knack for the way to deal with the two object situations. Okay. So let's go ahead and talk about this one. So this one actually, in spirit, kind of follows the same thing that we were doing with Jimmy and David before. And that's to say we had two objects and we want to find out how long it takes for them to get to the same place and what that place is. So in order to do this, what we say is we have two position equations, one for me and one for the bus. And initially, the bus is 8 meters ahead of us, and it has some acceleration of 1.1 meters per second squared. And we have some initial velocity of, so this is the acceleration of the bus.
I think it's just 1.1.
It says what?
It's just one.
Oh, it's just one. It's just one. I don't know where I got 1.1 from. Probably another problem. So we have an initial velocity v0 equal to 5 meters per second. Okay? So in order to find these two position equations, what we want to do is we want to look at the general position equation that we have here, and then just read this off term by term. So when we do that, what we have for our position, initially we say that we start from 0. So no initial position there, it's just 0. Then we have the velocity term. So this is going to be the v0 that I have here times time. And then we're not accelerating. So that term is 0. For the bus, this has some initial position that we'll call x0 for now. So this is going to be x0. It has no initial velocity. It starts from rest. And so that second term is going to be 0. Then we just have the third term, which is going to be plus the 1/2 at squared. Now, in order for us to catch the bus, that means that this position and this position need to be equal to each other. And so this says that v0t is going to be equal to x0 plus 1/2 at squared. And so let's rearrange this so that we can solve it. So I'm going to move this to this side here and kind of write it in more of a canonical form here. So this says 1/2 at squared minus v0t plus x0 is equal to 0. And then what we see here is we actually have a quadratic equation. And this can be solved using the quadratic formula. So that's to say this is going to be negative b, which is going to be minus v0, so this is going to be v0 plus or minus the square root of v0 squared minus 4ac, so this is going to give me minus 2 because the 4 cancels into half, times a times x0 divided by 2a, which is just going to be a. So we actually haven't established whether or not we are going to catch the bus or not, because depending on the parameters here, it might turn out that we don't catch the bus. And the real key to whether we catch the bus is this term right here, and you might remember from your math classes, this is what's called the discriminant. And the discriminant can take on a couple of different, it's actually, the discriminant's the part underneath the root. That can take on a couple of different values or can behave in certain different ways, so that this can be positive, negative, or 0. So in order for there to be a solution to this that is real, this needs to be either 0 or positive. And so when we plug the numbers into this, we actually end up seeing that we get something that's positive, so we do catch the bus. And when we evaluate this properly here, we end up finding that the time that we have is going to be about 2 seconds. Okay? Now, yeah.
When solving that, I also got like the time is 2 and the time is 8. So in that case, I choose the number.
So what does the 8 represent? Okay, good. So there are two solutions to this, right? You get a 2 second, you get an 8 second. Well, what does that mean? It means that I can run up to the bus and catch it, but I'm still running faster than the bus is moving, so I run past the bus. And then the bus catches me again. So that's what the 8 seconds means, which ideally is not what you want to do, even though the physics tells you it can happen if that's how you're moving. Okay? So when we use this 2 seconds, we end up finding that the total distance that you cover is going to be 10 meters. Okay? So we have a worksheet here at the front. Please pick this up on your way out. It's going to be due next Thursday.